I'm going to record. I'm sure a few people are going to probably join us as we go, and that's okay. So today in the module, there's a PowerPoint 7 and 8. If you want to follow along and write on it, cool. We're also going to go through a couple of cool, what are they called? Basically like simulations in the textbook. I want to show you those. So I'm going to try to show you those to help get this stuff down. But what I want you to understand is that when we go through energy, we have to understand what work is, how forces lead to energy, and then what we're going to end up with is really one equation, just one equation that you write down. So we're not even really going to need to draw free body diagrams, any of that stuff really. You can almost just write down the equation. However, each part of that equation, we need to understand what it means, where it comes from. So I'm going to get started by talking about work. And there's something called a work energy theorem, which is central to all of this. But to understand how we can use energy to basically find the motion, remember everything we do in this class, this whole class, everything we do is about motion. You're trying to find the velocity, or you're trying to find the acceleration, or you're trying to find the position of a system after some amount of time had passed, or the initial position of a system, or whether it was projectile motion or a block on an incline or a cell in bloodstream. Everything we do is about motion in this class. And the nice thing is energy basically gives you the motion right away. You can almost just write it down and you're done. So you might be asking, why didn't we start with energy if it's so simple? Well, we had to understand what forces were. So we had to kind of have a understanding of forces and how acceleration and velocity and displacement all work. Some of you have taken either physics or chemistry before, and you might be at least familiar with the idea of work, particularly work when it involves an ideal gas, changing the volume or pressure of an ideal gas and doing work on a system, or the system doing work on the environment. That is related to the work that we're going to talk about. In fact, they're kind of the same thing, but very different, because we're not talking about gases, we're talking about solid things. So let's start off by talking about what is work. Just what is this idea of work in physics? So before, we always drew forces. That was the whole point of the free body diagram, was you drew the forces and we had to assume some direction of acceleration. And while we didn't explicitly really get into the vector stuff at all, I mean, everything was vectors, but we didn't worry too much about the vectors. We're going to worry a little bit more about the vectors now. So what is work? Well, if you apply a force over a certain distance, so if I apply a 5 Newton force over a 2 meter distance to a mass, I do work. Work is the change in motion, the change in velocity, we'll see, of a particle due to, or system, due to a force acting on it. So what we can do is we can define work in vector analysis terminology as the dot product between a force and a displacement. We'll talk about what that means. It's why I wanted you to find the components. Remember that the dot product, if we do a dot product, the dot product of A dot B is AX, BX plus AY, BY plus AZ, BZ, et cetera, et cetera, et cetera. What that meant, though, was that we were multiplying the parallel parts of two vectors. So what work is it's the parallel part of a force in the direction of a displacement. So if we push a block from rest, let's say we have some block, let's say it's you're trying to push a box across an icy floor, and you're pushing it in the X direction. And so it moves in the X direction, some change of X. If we want to know how much work we do, well, the work is F dot D. And we see that F is whatever its magnitude is in the X hat, and D is whatever the change of X is in the X hat. So F dot D would just be F times the change of X. Here our F would be 2 newtons, our distance would be 2 meters, and what we would get is we'd get 4. Dot product is a scalar, and the units of this would be newtons times meters, force times distance, obviously. Now, what is a newton meter? So a newton meter is something called a joule, and a joule is one of the special, maybe the most special units after newtons. Newton meters are joules. They are the unit of energy. And the nice thing about a joule is if you remember that it's a newton meter, you'll always remember it's force times distance, right? Energy is a scalar. That means you can talk about negative energy, but when you say that, what you're talking about is taking energy out of a system. For us, what that would mean is you would be reducing the velocity. So if you speed something up, you put energy in. We're going to talk about kinetic energy in a minute, but for now, if you do positive work means positive energy, which means speed goes up. Negative work means negative energy, which means speed goes down. And we'll see that. But it's really important that you understand force times distance is energy, newton meters, joules. All right, we need to talk about this again really fast. The dot product is A dot B, which is magnitude of A, magnitude of B, cos of the angle between them, which is also AX, BX, plus AY, BY, etc. However many things you have. We have 4 cases of the dot product to worry about. So the first case is if they are in the same direction. So let's say we apply a force while an object moves a distance d, they're in the same direction, right? D is in the same direction as F. Therefore, the angle between F and D, if we draw these as vectors, there is no angle between F and D. Cosine of 0 is 1. This dot product is just F times D. A lot of times that's what we're going to have. We're going to have a force moving something in a direction, and all we have to do is multiply the force times the distance that it was applied. You can kind of think of it as how long it was applied. However, when we apply a force for a certain amount of time, we get something totally different. What we get is something called an impulse, and the impulse leads to momentum, which is chapter 9. So for now, we're talking about work. We're talking about energy. If you apply a force for a distance, you get energy. And we'll talk about what that energy is in a minute. What if, however, the force and the displacement were perpendicular? The best example I can think of is you're trying to push a car. So you're trying to push a car with some force and you're actually pushing up. And you're trying to make the car move in the X direction, but your force is in the Y, right? Well, in this case, because you can't, presumably, you're not strong enough to lift the car off the ground. In this case, F dot D would be 0, there is no F of X, times D, plus F times 0. This is F in the X, this is D in the Y. You get nothing. A force that acts perpendicular to the displacement gives you no work. Now, a much better example is the example that they always talk about. I don't know why my camera's so dark. This is the example they always talk about. If you lift a weight off the floor, you do work. The reason you do work is you are moving the object against gravity. It's not about you lifting. Obviously, you have to do the work. But as the object gets lifted, D is up and the force of gravity, which is mg, is down. And the work is force of gravity dotted with D. Now, obviously, this is negative mg. So this is negative mg times however high you lift it. You do negative work. It costs energy to lift something up against gravity. You know that as a human, though. You lift something up, you use energy. The energy you're using is in your muscles, it's chemicals, food, all that. We don't really care about where that energy is coming from, only that it's going to cost energy to lift something against gravity. However, what about moving at a constant velocity across a room? And the only force we're worried about is gravity. So we take our object and we move it some distance d, while the force of gravity is down in the y direction, right? So we move it in the x direction, but the force of gravity is y. How much work do you have to do against gravity? None. Your force is not, or the force and the displacement are not in the same component. They're not in the same direction. They're perpendicular to each other. So the idea here is that perpendicular forces don't do work, or you don't do work against perpendicular forces when you move in the x direction. You don't do work against forces in the y. If your displacement and your force are 90 degrees off, you're not working against it. And we'll come back to that. The final one, no, there's two more, sorry, is opposite direction. And as we said, if the force of gravity is down and your displacement is up, then F dot D here would be negative mg times D, or it would be mg times D times cosine of the angle between them. But the angle between that force and D is 180 degrees. Cosine of 180 is -1. So when you do work with I should say, when your displacement and your force are in opposite directions, you get a negative sign. Why? Let's try to think about this. If I push my block in the same direction that it moves, I do positive work. That's because F and D are in a parallel direction, same direction. But what if the block was already sliding this way? So it's moving this way, but I'm trying to slow it down with some force, acting in the opposite direction. Here, when F and D are anti-parallel, meaning they're in opposite directions, I get negative work. I slow down the object. Negative work takes energy out of the object. And we'll talk about what that energy is in a minute, but yes, the work is the energy of the system. We'll get to that. I'm going to actually derive that in a minute. But for now, we can just think of doing negative work slows an object down. Doing negative work implies that you apply a force in the opposite direction to which the object is moving. If this object were moving to the left and the force were to the right, negative work. If the force and the displacement are in the same direction, you do positive work and it speeds up. All right. The final case, like all of these, is that if instead I apply the force at some angle, right, and then D is here, and I want to know how much work is done. We can think of this as resolving into two different forces, a force in the Y, a force in the X. D is in the X here. So just like before, we can resolve this into F sine theta, F cos theta. But we see here that we know that the definition is F dot D, and that is F D cosine of the angle between them. Another way of stating that is that the work is F of X times D, meaning because D is in X, we take the component of F in the same direction as D, and that's our dot product. That's why I had you guys worry about that so much on the vector lab, finding the component of a vector in a certain direction. The two vectors here are F and D. We need the part of F parallel to D to figure out how much of that force is actually making it move. Again, think about moving a fridge, if you've ever had to move a fridge. If you're pushing up at some angle, only some of that force is moving that fridge across the room. If you push straight in the horizontal, all of your force is moving it. However, if you're at some angle, only some of the force is going to make the object move. We'll come back to that when we do problems and you'll see. So.
Professor?
Yes.
So for case number 4, you were saying, you basically said that we have to find like the component of that's parallel to D, because that's how much force of F that is actually like moving the object forward, right?
Right. So basically what we're looking at is just the definition of the dot product. The definition of the dot product for any two vectors, A dot B, is really saying this is the same as A in the direction of B times B, or A times B in the direction of A. So just bear that in mind. There is a physical significance to that mathematical equation. And that physical significance when we're talking about work is that it's force dotted with distance. And the only way a force can do work is if part of that force is in the same direction as the object is moving. If it's in the same direction. Yeah, go ahead.
Well, I was just going to say, because on case number 2 or something, you said that perpendicular forces don't like, you don't work against perpendicular forces.
Right.
So
They do no work.
Yeah.
Basically, if you think about it this way, if you're moving in the X and you have some force acting on you in the Y, but you can't leave the Y, right? You can't go up or down in Y. You can only move left or right. Forces in the Y aren't going to do any work to you, right?
Right.
They're not going to make you move. They're not going to make you move at all. They're not going to change your speed. Remember, a force is really mass times acceleration. So what we're talking about here is that the force has to be in the same direction as displacement to speed it up. If the force is in the opposite direction of the displacement, it slows it down. That's all I want.
That's negative.
What's that?
Yeah. And that's negative work, right?
Right. But that in vector notation means that the two vectors are 180 degrees off each other. They're
Yeah.
pointing in opposite directions. It'll make more sense once we actually start using the definition of work, but
Yeah.
we can actually do this as an integral. And f dx, if you want to put a dot, this is really what it is. And we integrate from x initial to x final. However, we're going to do a couple of little tricks here. We know that f is ma for any force, and that ma is dB dt. So let's rewrite this as m dB dx over dt. This right here is v. We know that. We know that this is v. So we write x initial, x final is mv dv. And now, since we've changed this, we need to change these to v initial and v final. We've changed our integration. So doing this, though, is super easy, right? It's just mv squared over 2 from v initial to v final. So the work is mv final squared over 2 minus mv initial squared over 2. That quantity right there, mv squared over 2, is kinetic energy. That's saying that if we apply a force for some distance, we get a change in kinetic energy. If you don't believe this is kinetic energy, it's actually energy. mv squared over 2 has units of kilograms, meters squared over seconds squared. Remember that a Newton is a kilogram meter per second squared. So if I multiply this by another meter, I get energy.
Yeah.
Kinetic energy is definitely energy. And that means that the work that we do, any force does, ends up being the change in kinetic energy. Do not forget that the change of anything is A final minus A initial. So what this means is force dot distance gives us mv final squared over 2 minus mv initial squared over 2. Period. That is the work energy theorem. That says that work becomes energy. And that's, if this were negative, then this term would be bigger, right? Which would mean it slowed down. If this is positive, this term is bigger, v final is bigger, and that means it sped up. It's all right there in this nice little integral, but we don't have to worry about that. What we have to worry about is that if you're given, let's go back to that example where we had the 2 Newton force over 2 meters, and these are both in the x hat direction. So we're sliding a box a distance of 2 meters using a force of 2 newtons. This would say that the work is F dot D, and that that's equal to mv final squared over 2 minus mv initial squared over 2. Let's assume it starts from rest, although we don't have to. That means that this is 0. And what we get is we get 2. Oh, and I do need a mass here. My mass will be 2 kilograms. I know everything's 2. 2 times 2 is equal to 2 v final squared over 2. These become 1. So I get 4 is v final squared, or v final is 2 meters per second. So all I've done, I needed a mass and I needed to know what v naught was. All I did though was I said, okay, I applied a force for 2 meters, a force of 2 newtons. What was my change in kinetic energy? Well, my change in kinetic energy, m is 2 over 2 squared. This is 4 joules minus 0 joules, because this was 0. So my change in kinetic energy was 4 joules. My change in velocity was 2 meters per second. But you can see that really all you have to write down, if you know, all you really have to write down is the force dotted with D is mb final squared over 2 minus mb initial squared over 2. That's the only equation here so far. We're going to have a much bigger equation later, which is a lot easier. But for now, for work, that's it. It's plug and chug, to be honest with you. You might have the forces at some angle, so you need to put in F cosine. But it's pretty simple. A lot simpler than dealing with accelerations and free body diagrams and all that. You don't really need to do that. If the force is not constant, we're going to talk about constant forces for the most part, but let's say it's not constant. I give you some force. For example, the force is 4x squared minus cos of x. What is the work? Well, all you have to do is integrate x initial to x final f dx, which means you just plug in your force. Here it's 4x squared minus cos theta dx. Doing this integral, kick that one up one and divide by the new. So this is 4/3 x to the third. Going up is what, sine? So minus sine, yeah. Oh yeah, I see what it, sorry. It's minus sine of x, and then going from whatever x1 is to x2 or x initial to x final, is what I did here. Would be all you'd have to do. It's not hard if you have a general force. And then remember that this integral is still going to be equal to mb final squared over 2 minus mb initial squared over 2. No, it's so the derivative of sine is cosine. Therefore, going backwards, going from cos to sine is positive. There's a negative sign in the integral.
Oh,
yeah. If we were going the other way, if we were going sine to cosine, it would be a negative.
Yeah.
I always mess that up too, Lucas. So double check.
Well, because taking the derivative makes more sense, but going backwards for some reason confuses me.
Yeah. What are the units after we take the integral? So the units of work are always Newton meters, which are joules, Shota. Joules. Joule was a like turn of the century, maybe it was mid 1800s. Really engineer on steam engines, and he's a cool guy. But the joule is the unit of energy. Always keep that in mind. Newtons times meters are energy. All right. So if we have a constant force, as I said, you just can plug in ma, which is mdv dt. You can move the dt under the dx, and you get mb dot dv, and you get that, which is awesome. That just means that work is change of energy. So kinetic energy, mv squared. I don't know, what did I do with the 3 in the denominator? I forgot it. I actually did that integral wrong. I did that integral as a derivative here. This is wrong. This should be this should actually be 4/3.
The integral is correct, but you missed the 3 at the denominator.
Yeah, but this would kick up one though, so it would be to the third, and it wouldn't be that actually. It would be
that one.
thirds.
Yeah,
it's not that important. All I was trying to get at was that you can just plug in the force as an integral and go from x initial to x final, where if this is some function of x, you just plug it in for any general force. We won't do that though. We're going to assume that everything's constant, and when things are constant, this is what you get, which is nice. it makes it a lot easier. The reason why we're going to assume constant forces is because things like friction, we're going to take to be constant. We're almost never going to have to deal with a weird force. So we're not going to really have to integrate. But if you did, for some reason, if you're working, doing research on something and you need to integrate the force, the integral is f dot dx. The other thing to remember is that the area under the curve is the integral. So f times dx is the area under the curve, right? It's the energy. What are you talking about, Sammy? Does V2 equal mv final squared over 2? On this page? Sammy? So I don't know what you mean though. V2 is V final, same difference. Oh, okay. So the work is mv2 squared over 2 minus mv1 squared over 2. Another way of writing that is mv final squared over 2 minus mv initial squared over 2. However you prefer, I don't care. I alternate. So kinetic energy. As I said, this is probably the most important thing not to ever forget. This delta KE always means final minus initial units energy. Delta KE is mv final squared over 2 or v2 squared over 2 minus v1 squared over 2 or v initial squared over 2, whichever way you want to call it. And as I've said, the work is the change in kinetic energy. If the work is positive, then mv2 squared over 2 is bigger than mv1 squared over 2, and it speeds up. The velocity increases. If the work is negative, then mv1 squared over 2 is bigger than mv2 squared over 2. The object slows down. We're going to have a concrete example starting with two particular forces. The reason why there's two of them is there are two forces which are called conservative. These conservative forces are very special. I'll tell you why in a minute. But for now, to get this whole thing down, I want to do an example with gravity again, right? So think about dropping an object. You're dropping an object from rest from a height of 5 meters, okay? And this object is a 1 kilogram object. So you're dropping it with an initial velocity of 0, and you want to know what speed it hits the ground. Now, remember before we did this, we wrote down the constant acceleration free fall equations. We don't have to do that here. Here, we know that the force is mg and it's down, and we know that the displacement is y, also down. So the work is F dot D, which is mg times the height. These are both positive because they're both in the same direction. You could actually write this as mg in the negative y hat direction and h also in the negative y hat direction because it went down a distance h. Or you can just realize that they're both in the same direction, so they're both positive. That is going to be equal to mv final squared over 2 minus mv initial squared over 2. Taking this was at rest. If I want to know what v final is, I see that mv final squared over 2 is equal to mgh. Get rid of my m's. V final is 2gh. That is exactly what we found when we did it with the equations for free fall. If we think about this one, v final squared minus v initial squared is equal to minus 2g y final minus y initial. This would be 0. Y initial would be h. Y final would be 0. I would get b final is 2gh, which is exactly what b final squared, which is exactly what I got there. It's actually really nice that you don't have to remember anything. You just have to remember what the force is, how far the force was applied, you know, what distance you applied the force for, and that it gives you a change in kinetic energy. That is so easy compared to remembering all those stupid kinematic equations that we remembered for free fall. This works for anything. However, gravity is special. So what happens if instead you want to throw a ball up to maximum height? So it ends up at h, mg, force of gravity is down, the displacement, h is up, it went a distance h, mg was down, v final, we know is 0 at maximum height. V initial, let's say, was 10 meters per second. How high can you throw this thing? Well, the force, mg, is in the negative y hat direction, times, or dotted with, h in the positive y hat direction. That is negative mgh. That is equal to mv final squared over 2 minus mv initial squared over 2. This is 0 because we're at max height. Canceling negative m from both of these, I get that gh is v naught squared over 2, or h is v naught squared over 2g, which was exactly what we found before. V naught squared is 100 divided by, let's say g is 10, close enough to 10. 100 divided by 20 is 5. It went up 5 meters. That is exactly the same equation you would have gotten using the free fall equations, but we just used work and energy. It's really nice. It's even nicer when we get everything combined, which I'll show you. But you might have noticed that in the example where we dropped it, the work was mgh. In the example where we threw it up, the work was negative mgh. Why? As it fell, it gained velocity. As it fell, gravity did positive work because gravity and the displacement, the distance it traveled, were in the same direction. Gravity was causing it to speed up. It was doing positive work on the object. As it went up, gravity was doing negative work. The displacement of the object and the force of gravity were opposite of each other. So gravity caused it to slow down from 10 meters per second to 0 at maximum height. So if we do the full free fall, as it goes up, force of gravity does negative work. And as it falls, force of gravity does positive work. Slows, speeds up. And that's all there is to this, is you just consider that the force does work in the direction of travel, or opposite, and that work immediately translates to a change in velocity or a change in kinetic energy, whichever way you want to see it, which is really nice, really nice. However, we're not quite done here. And this is just saying all of that. Now, let me ask you this. Let's say you slide across the ground, right? So as you slide across the ground on like wet grass, let's say, how much work does gravity do to you? Well, the force of gravity is down and your displacement is in the x direction. Gravity does no work as you slide along the ground. It's not speeding you up and it's not slowing you down. Gravity is doing nothing to change your speed. if that makes sense. Mathematically, how we describe that is the dot product and the change in kinetic energy. So I hope that all makes sense. I'm going to go and check something. This is in our Wiley course resources. I urge you to check these out. But in chapter 7, you not only have the book, you have a bunch of cool videos and references and animations. I want to show you, is this the one? Nope, that is not the one I wanted. It's difficult to label these, and I wish they would let you just link them. So this is projectile motion. Now, as we go, I want you to look, the arrow straight down is the force of gravity, right? And then this will be the work done by gravity. You can go, you have access to all these. So as it goes, so it first takes off, gravity is already doing negative 400 joules of work as it slows it down from its initial velocity. Eventually, when it gets to the top, gravity evens out. The slope of the work done by gravity becomes 0. Right at the top, the work of gravity is 0 because it's traveling essentially instantaneously horizontal. Then, as it begins to descend, gravity is going to start doing positive work, right? So the slope of this is going to be positive. And eventually, gravity will have done 0 work when it comes back, which is weird. But essentially, when it hits the ground, it's going to have the same velocity that it had initially. So what this graph is really showing is the total work done by gravity. As it goes to here, it reaches the maximum, and then the work done by gravity starts reducing down. There's probably a better, I don't want to do that one. We'll get to work on it, spring. Yeah, there's not a great one here. No. The let's go back to that. I misspoke. I confused you. I'm sorry. Nope, that wasn't what I wanted. Work done in. Where did that stupid thing go? Oh, right here. So the work done by gravity is going to slow the object down. Now remember, in projectile motion, in the y direction, at the very top, the y velocity is 0. So it starts off with some positive y velocity that reduces to 0 at the top of the motion and then increases negatively until it hits the ground. If the initial and final height are the same, then the velocity in the y direction will be flipped when it hits the ground. Whatever the initial y velocity was, the final y velocity is that velocity with a minus sign. So the work done by gravity is going to be mg times the change in height. But as it goes up, the work done by gravity will be negative because gravity and the displacement in the y only, the displacement in the y is positive up, gravity is negative down, the work will be negative. Once it reaches the top, it reaches the maximum work that gravity will have done. Here it's minus 1223 Newton meters, 1223 joules. As it starts to come back down, this is showing the total work done by gravity. That's what this is showing. As it comes back down, gravity is starting to do positive work. So this amount is going to be reduced back to 0 when it hits the ground. Why will the work done by gravity, the total work done by gravity, be 0 when it hits the ground? Because all the negative work it did going up is equal to all the positive work it did coming back down. I wanted a one-dimensional free fall, but I guess they don't have one. So maybe I'll just do one. Well, we'll do one in a bit. Because I'll show you that. I believe I have a problem that shows that. Right. If there's no change of displacement, there's no work. So if it doesn't move, if you apply a force and it doesn't move, that force did no work. Or if you apply a force and it moves perpendicular, that force does no work. We'll do a few examples in a minute. So there are 3 cases for the work done by gravity. If the object travels upward, meaning in the positive y and gravity is down, the object slows down. You can do this right here. Toss your pen up in the air. It slows down as it goes up because gravity is doing negative work on it. Gravity is changing its kinetic energy negatively, reducing its kinetic energy. If you drop an object, it speeds up before it hits the ground. That's because d is down in the negative y direction, but so is the force of gravity. Therefore, because they're both in the same direction, it speeds up. Gravity, we say, did positive work. Now, if the object only travels in the x direction and gravity is in the y, then it's unaffected by gravity, right? The force of gravity can't be doing any work to the object because it's not speeding it up or slowing it down. So if its y displacement doesn't change, gravity did no work. It's not the whole story because gravity is a conservative force. And what's really cool about a conservative force is it's path independent. What does that mean? That means if there's a hill at a height h and you go straight up to the top. So let's say you walk and you go straight up. How much work was done? And let me do this. How much work was done going up to the top? mgh. That's how much energy you required to go up to the top. Force times the distance. We would actually say that the work is negative because mg is down and h is positive up. So it cost energy to go up to the top of the hill. Walking up a hill requires energy, but we would use the same energy even if we had to go up a ladder and come back down and then come in here, because we gain energy coming down. If that's confusing, essentially, you don't care what path it takes to get there. Trying to think of a better example of this. Anyway, I guess the best example I can give you is actually a mathematical one. It turns out that when you have a conservative force, right, and you're moving from H1 to H2, right, that if you go like this, or you go like this, or you go like this, and come back, no matter what path the particle takes, the only thing we care about is the endpoints. We only care about H1 and H2. That's what makes it conservative. So if that's true, then we say that the potential energy of an object for a conservative force is H2 minus H1. All right, this is where things are going to get a little bit tricky, and then it's going to get super easy. It's going to make sense in a minute. Let's talk about the work done by gravity, assuming that gravity points down and y is positive upward. If that's the case, the work done is F dot D and we're integrating it, which means that we're doing it in the y direction. So we get negative mg dy. That's what it's showing here, from y1 to y2. If we integrate this with respect to y, what do we get? We get negative mg y2 minus y1. Move the negative sign inside, you get mg y1 minus y2. The negative sign coming inside changes it. So what that means is, remember, we said mg y2 minus mg y1 was the change in potential energy. They often state it in physics as the work done by gravity is minus the change in potential energy of gravity, which is mgy1 minus mgy2. What does that do for us, though? That does something really, really cool for us. I'm going to show you that right here. The work is also the change in kinetic energy. So mgy2, sorry, y1, minus mgy2, this was our definition of the work done by gravity, is equal to mv2 squared minus mv1 squared. Another way of saying this is the negative change of the potential energy of gravity is equal to the change in kinetic energy. But there's something really simple here. I need all of you to pay attention. If you're not paying attention and you're kind of doing other things while you're watching this, pay attention to this right now because it's super important. Look at this equation right here. This is what makes energy so easy to use. Put all the 2's on one side and all the 1's on one side. You get mv1 squared over 2 plus mgy1 is equal to mv2 squared over 2 plus mgy2. Everything's positive, which means that if I choose, and I'm going to do this with gravity, if I choose an object drops from height, so let's say y1 is equal to h, which is equal to 5 meters, y2 is equal to 0 meters, b initial is equal to 0, and b final, I don't know. All I have to do is choose 2 points. I'm calling this point 1, I'm calling this point 2. I write mv1 squared over 2 plus mgy1 is equal to mv2 squared over 2 plus mgy2. Here, v1, I called this v0. Let's call this v1 and v2. Sorry, guys. This is 0, this is h, this is unknown, this is 0. Cancel the m's, I get that v2 is square root of 2gh, as before. But all I have to remember, the only thing I have to remember is to write down the kinetic energy and the potential energy of gravity at 2 points. I pick 2 points where I know the height, and maybe I know one of the velocities, and I can find the other velocity. I pick 2 points where I know the velocity change, and maybe I don't know the height. I can pick the height change. But the only thing I need to remember is mv squared over 2 plus mgh. That's it. As long as you know that h is the height change, and you can find it, we'll talk about this. Imagine going up an inclined plane. Your height is not the same as the distance up the plane. Your height is your height because you're working against gravity. Let me show you what I mean. The only time this gets tricky is imagine sliding down an inclined plane. And let's say this is 30, and I know that this length is 10 meters, 30 degrees. And I want to know when it slides to the bottom. So I pick 2 points. I'm going to pick this one, and I'm going to pick at the bottom. What I write down is B1 squared over 2 plus mgh1 is equal to mb2 squared over 2 plus mgh2. Now, I know that B initial is 0. I know that the height, I'm going to call this B1 actually, starts from rest. I know that height 2 is 0, but what is height 1? It's not the distance up the plane. This is got to be h1. Now, h1 here would be hypotenuse times cosine, so 10 cos 30, whatever that happens to be. And I picked a bad number. I should have probably picked 60 because that's easier. But 10 cos 30 is 8.66. 8.66. So I
Excuse
know,
me,
yes.
the height is 10 sine of 30 degrees, not cosine.
Oh yeah, you're right. Yeah, I'm annoying myself. Sine of 30 is a half, so this is 5 meters. Yeah, I think my brain was actually trying to tell me it was sine and I was being dumb. And I decided. Anyway, he's right. Hamid is right. It's 10 sine 30, 5 meters. So we know H1, we know H2, we know B1 is 0 because it starts from rest. This is mgh1 is equal to mb2 squared over 2. This means that B2 is square root of 2gh1, which is square root of 2g 10 sine 30. So we found that without having to do a free body diagram at all, without having to decide, oh, we're going to break up the weight and we're going to, find this normal force and we're going to find this and we're going to find that. That's kind of amazing that all we had to figure out was the change in height because we needed it for the work done by gravity. And we solved it. Essentially, what we really did was we found the change in the potential energy when we went from 1 to 2. And we found the change in kinetic energy, but we can set it up in this really nice form where all we have to remember is kinetic energy and change of potential energy. Now, physically, what is going on here is that actually the change of potential energy is becoming the change in kinetic energy. So when we went from here to here, so from 1 to 2, we had a potential energy of mgh1, and then, so we want to know the loss. So mgh2 minus mgh1 is equal to however much potential energy we lost had to become the kinetic energy. And I have that flipped, which I shouldn't have that flipped. Okay, so mgh1 minus mgh2 is mb1, mb2 squared minus mb1 squared. So this is the change in kinetic energy. This is minus the change in potential energy. That's the reason why there's a minus there, is because gravity works down. Gravity does work in the negative direction. Gravity does work when you fall, so it has to be the negative. What was our change in kinetic energy here? Let's say our M was 2 kilograms. I didn't say on this original one. But we know that this went from 2g, we said 5 meters, to 0. So let's call G 10. This was 100 joules. 2 times 10 times 5 is 20 times 5 is 100. This is 100 joules. Therefore, we should have gotten an increase in kinetic energy since this was originally 0. This should be 100 joules. Is it? Well, we said that B2 was, oh, we didn't find it. But we could find it really fast by M was 2, so this is really equal to B2 squared. It's 100 joules. Take the square root, and we get that B2 is 10 joules. I'm sorry, 10 meters per second squared. Stop. Yeah, and you absolutely can. You can get rid of m if you want, so that you would have basically g h1 minus g h2 is equal to v2 squared over 2 minus v1 squared over 2, or even multiply through by 2 when you get 2g. But let's look at that for a second. What is this? v2 squared minus v1 squared is equal to minus 2g h1 minus h2. Did I flip that the wrong way? Why is that flipped? I feel like I have something flipped.
Because you put negative in front of the 2. And you
Oh
should
yeah,
put the 2
absolutely.
minus h1.
Absolutely, yeah, you're right. I put the negative in front of the 2. So this equation you already know though, right? That equation is the equation from v final squared minus v initial squared is minus 2g y final minus y initial. That was from projectile motion. Multiply through by m and divide through by 2, and I get mv final squared over 2 minus mv initial squared over 2 is equal to minus mg y final minus y initial, which if I redo this, I get mv final squared over 2 plus mg y final is mv initial squared over 2 plus mg y initial, which is the energy equation, which is really nice. But the really nice thing about it is all you have to remember to do is write the kinetic energy and the potential energy. Mgy is the potential energy at any point. We said that gravity was a conservative force. That means that if the only thing we care about is kinetic energy and gravity, if we have no other forces except gravity, this is always true for any 2 positions, anywhere on the surface of the Earth. A change in the height gives you a change in the velocity. It's really, really nice. That's conservation of energy and the work energy theorem, all working together to give you something that you can basically write on the back of an envelope to solve, to figure out how fast something's going to hit the ground if you drop it, or how high up it's going to go in the air before it stops. It's
Professor,
yeah.
why like my reasoning might be wrong, but why wouldn't we learn energy before kinematics? Like I feel like it makes more sense to learn about energy and then learn this equation.
And in some countries they do. In fact, I'm being a little bit, I haven't told you the whole story. There's something called Hamiltonian mechanics, which you're going to learn if you go on to chemistry or physics. Hamiltonian mechanics uses the energy, this exact energy, the kinetic and the potential energies, to get a differential equation and solve all sorts of cool things. Energy is a lot easier, but you're going to be even more matter when we do chapter 9, and you realize that well, let me, a small digression.
Okay.
We said that Newton said F is equal to ma. We lied. We completely lied to you. What Newton said was F is equal to m dv dt, but he also put the m inside, which is really dmv dt. This cool thing, well, let's actually integrate this, right? So we get force dt is dmv, and we want to integrate this. So this becomes something force times time, which I'm just going to say is something called an impulse, but
Mhm.
this ends up being the change in MV. MV is something called momentum. And it turns out that momentum is conserved unless there's an outside force acting, which you can see right here. If F is 0, there's no change in the momentum. If we take our system to be big enough that there's no outside force acting, everything is internal, well,
Mhm.
then there's no change in momentum, which means that we can add up all the momentum before and after, and they have to be equal. And that turns out to be so much easier than anything else we've done. It's easier even than energy to understand. In a collision, two things hit and bounce off. The total momentum before they hit and the total momentum after they hit have to be the same. And so you can find all sorts of cool things. And the collision itself is internal forces, which means we don't care about what happened during the collision. We only care about before and after. And you're not squaring anything. You're simply writing M1 V1, M2 V1, or M1 V1 initial plus M2 V2 initial is equal to M1 V final plus M2 V final, you know, their final velocities. It's so ridiculously easy. So what Newton actually said was that forces cause a change in momentum and that everything is momentum. And momentum's super easy. And for almost every case, you can usually find when it's conserved, and it's literally the easiest thing in the world.
What's like a good definition for someone that doesn't like I've heard the word momentum and I kind of know how to apply it, but like what's like the actual definition of it?
Now, and here's the bad thing about it. It's mass times velocity, and mass times velocity has no units. There is no kilogram meter per second unit. It doesn't have a unit. It's momentum, which is really weird to me. It's one of the weirdest things in the world to me is that momentum never got a name. Newton's got a name, joules, for energy. Momentum's really important. It doesn't have a name. There's people online that call it moms. Momentum, it does not have units of moms. It has units of kilogram meters per second. There's also something called angular momentum, which has to do with how something rotates. And basically that if you don't supply an external torque, it won't change its rotation. So basically, what Newton really said is an object has momentum, mv, and unless you apply a force, that momentum never changes. The weird thing about momentum, though, is those of you who are really observant might realize that if this is true, that means that mass can change. And yep, mass can change. Mass could be the thing that's changing if the momentum's changing. And we'll talk about that.
Is it because it's dmv? Like, because when you're integrating something, it's dx, so it's like delta x. But now
you normally think of this as MA, but it's
yeah.
also completely okay to have this be true.
But why can you do that?
Because
Like,
it's true. It's
oh,
the momentum changes if the mass changes, and the momentum changes if the velocity changes. We'll talk about it when we talk about the rocket equation, which is, I believe, next time. Chapter 9, not next time, but next week. People actually didn't think that rockets could fly in space. And it turns out that the momentum of the fuel leaving the rocket actually imparts momentum to the rocket itself, because some of the rocket's mass is leaving with momentum, but conservation of momentum says the system's momentum can't change without an external force. So if you have negative momentum that way, you have positive momentum this way. And we're going to see how that works. And it turns out to be so simple and really cool. And you might start to realize that some of this stuff is deceptively simple. The hard part starts to come in when you essentially have many, 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 many objects. We'll talk about that though. So
Yeah.
this energy stuff gets
Mhm.
hard too when we have too many objects. We're going to talk about it, but imagine that we have a whole bunch of masses. We had 10 masses connected by ropes. You would have to write down the kinetic energy and the potential energy of everything, and we'll get to that.
When you say mass changes, do you literally mean that the object gets lighter or heavier?
Have you ever seen a where they put the what is it called, Mentos in the bottle of soda?
Yeah.
Yeah, as it shoots the soda out, the bottle itself is getting less mass. It's actually losing mass as it shoots the soda out. And you could set it, like drop the Mentos in and set it on the ground. It'll shoot itself across the ground because the soda is flying out the back, and that's causing the bottle to shoot the other way. Whatever momentum the soda leaves with, the rocket or the bottle, the 2-liter has to carry the other way. Really cool and really easy to do, really easy to write up, but really strange, odd. We're going to start getting to stuff that you're going to start asking yourself, like, why does it work this way? And I don't always know the answer to that. Anyway, so from all this, as I said, you get this equation. And the beauty of this equation is that, let's say again, we have an object that falls. You could choose H to be 5, H to be 4, H to be 3, H to be 0, any two of these, and plug them in. And if you knew the velocity at the beginning, you could find, presumably, the velocity at the end, right? It's super nice. You just choose any 2 points that you know the most information or that you care about, and we'll come to that. So we say that K, the kinetic energy and the potential energy at any time, is something called the mechanical energy. If the potential energy only depends on gravity, which obviously that's the only thing we have, then mechanical energy is always conserved. And that means that E1 is equal to E2. The total kinetic energy at position 1 plus the total potential energy, and I say total because we could have multiple masses, and we'll do that one in a second, is equal to the total kinetic energy plus the total potential energy at part 2. Now, particle is launched with an initial 25 in the y. What maximum height? We've already done that one. But there is a really, really important idea here. So I want to, why did you do that? I want to do something kind of important here. There's a not great, not great example on one of those simulations is not the best that shows this. So I want to explain this to you. So let's say that we're going to say that Y1, we're going to call that 0. And Y2, we're going to say it falls negative 10 meters. Okay. So what we do, and we know that at B1, we're going to drop it from rest just to make this simple. We chose 1 and 2, and we say, okay, M1, nope, M G Y1 plus MV1 squared over 2. And we just set that equal to MG Y2 plus MV2 squared over 2. Now I said that Y1 was 0 and it started from rest. So that means that this is 0. I can cancel the masses. And what I get is I get that V2 squared is negative 2gy2. All I did was I moved this over so this becomes negative gy2, and then I multiplied through by 2. So I get this. And notice that v2 is square root of 2 times g times negative 10. Now, here's the important thing. I can pick 0 to be wherever I want, which means I could actually instead call y2 0, and then y1 would have to be 10 meters. I can choose my 0 to be anywhere because honestly what matters is the change in height, the change in potential energy, not the actual height. But y always has to be positive in the opposite direction of the force of gravity. So when I do this, what would happen is I would get y1 would now be 10, so I'd have mg y1. This would be 0. y2 would now be 0, is equal to mv2 squared over 2. Cancel your m's, and I get that v2 is square root of 2g y1, where y1 is 10. And I'm sorry, I forgot the minus sign here. So this is 2g times 10, this is 2g times 10. It doesn't matter where you put your 0. The only thing that matters is the change. So in a way, you could write this as the change in kinetic energy is equal to negative change in potential, which is equal to minus mg y2 minus y1. You could find this, and that would give you m over 2 v2 squared minus v1 squared is equal to, putting that negative m, mg y1 minus y2, if you want. Which means that as long as you know the change in height, you know the change in kinetic energy. That's important. Sometimes Wiley will just tell you an object falls 50 meters. If that's all you know, then you need to realize that you can choose whatever coordinates y1 and y2 that you want, as long as you get negative 50. Why negative 50? Because it said it fell 50 meters. So if y2 is 0, then y1 is 50. Or if y2 is 50, then y1 is 100, because it had to fall 50 meters. Whatever you get so that you get 50. Yeah, it's pretty easy. That's just a side point that'll come up sometimes. Potential energy, this is all more of the same. I will say that this is one thing to remember. Notice that our potential energy is mgh, and our force of gravity, why does it keep doing this? Our force of gravity and our potential energy of gravity. So what is this? Well, if we want the potential energy and the force, how are they related? It is the derivative. I should actually probably call it the total since we only have one. ddy or ddx. So the force is actually the position derivative of the potential energy, and they usually put a u for potential energy. So we say that the F is du dx, if you've ever seen that. The change in potential energy with respect to x is the force. For those of you who don't get that, ignore it. Those of you who do get that, who do speak that language, the language of derivatives, that's a really important derivative. The derivative of the potential energy, how the potential energy changes with position, is the force. that means f dx is du. And if you want to integrate the force with respect to position, you get the potential energy, which is exactly what we see here. This is the force times position, or the work, gives us the potential energy in this case. Kind of cool. It ends up sticking around, but it's something that if you can recognize that, a lot of physics as we move forward and go on and on and on, the math is actually kind of an English definition of the physics. And I really want you guys to understand that first and foremost. If you're looking at these problems and all you're seeing are letters that you need to plug numbers in, you're seeing it the wrong way. In physics, math is a literal definition of the system. It's better to say the initial kinetic energy plus the initial potential energy is the final potential energy plus, or final kinetic and final. That the change of energy is zero. I should say the change of energy, which is equal to energy initial minus energy final, had better equal zero. That means that there's a constant or a conserved energy. Instead of trying to think of it as mv squared over 2 plus mgh, without thinking of what those terms mean. Yeah.
Does that also mean that derivative of negative kinetic energy is, could you also say that's force, or no?
Sorry. No. That should have a derivative or a negative sign, by the way. I forgot the negative sign. The derivative with respect to position of the kinetic energy, what would that be? mv squared over 2 with respect to, so this is dx dt squared times m over 2 times d dx. So you'd still end up with, you would end up with like v over dt. It's like the average force.
I just thought I'd make it.
Yeah, maybe.
Oh, okay.
No one ever does that though. I guess you would end up with the average force. No.
Yeah.
You would end up with the average force.
The book did say something about average force somewhere. So
Yeah. The change in kinetic energy is the average force, I guess. No one ever does that though.
okay, I just thought I'd make the connection because like the change in kinetic energy is the change in that negative change in potential force.
dvx
Potential energy.
of the kinetic energy would be dx of m over 2 dx dt dx dt. So you would lose one of these and you would end up with this being v, and you would end up with mv to the half times d dt, which would be ma divided by 2. But that's not really all that helpful.
Yeah.
I think so. Maybe that's why they don't do it, because it's just not actually helpful.
Why is it negative du now?
In the potential energy?
Yeah.
The potential energy, it's a negative sign because that's how potential energy works. Here's the thing that I really need to get through to you guys, and this will actually come up in chapter 13 when we do gravity. But what does potential energy mean? If I hold a ball 10 meters above the ground, I say that it has a potential energy, and it's not moving. I haven't released it. I'm just holding it there. I say it has a potential energy of mgh. And let's say it's a 1 kilogram ball. So I have 1 times, I'm going to use 10 for g, times 10. It has 100 joules of kinetic energy. Does it have energy?
Yeah.
That's my question. Does it have real energy? Can you feel that energy? No, not in this case. We'll talk about this in a minute, but why then, what is this potential energy that we're talking about? That's the energy that it could possibly turn into kinetic energy. Potential energy is how much energy it would turn into kinetic energy if we let it go. The cool thing is that if it were at half that height, so now it's at half that height, then it has mgh2, which is 1 times 10 times 5. So it's at 50 joules. And we move it down and then we move it back up. Here it has 0 kinetic energy. We let it fall halfway. Then it now has 50 joules of kinetic energy and 50 joules of potential. Goes back up and you lose all the kinetic energy. And it now has 100 joules of potential energy. So what's happening is potential energy is energy that could turn into kinetic energy if we allow it to. It's a little odd. It'll make more sense when we talk about springs in a second. But basically, in a gravitational field, however far you are from the surface that would stop you, you have that much potential energy. However, I can do something really weird. Now, I'm still at 10 meters from the ground, so it's still at a height of 10 meters, but now I want to know how much kinetic energy will it have when it's fallen 1 meter, right? So relative to here, if this is my 0 of potential energy, how much potential energy does it have up there? Well, it has mgh, but now h is 1 meter. So relative to this point, it has potential energy of mgh, which is 1, I'm going to say 10 for g again. 1, it only has 10 joules. Because I chose my 0 to be 1 meter below where I currently am. So potential energy is real and not real. It's basically a weird way of understanding that if you let it go, gravity is going to do work and it's going to convert the potential energy to kinetic energy. The work that it does is because it's gravity. Vice versa, if it goes up, gravity is going to do negative work. It's going to lose kinetic energy. And so we say it gains potential energy. It's weird with gravity. It makes more sense when we start talking about satellites and like moving off the surface of the Earth. It also, whether or not you realize it, when you get to electron and 4b, you're going to have potential energy between 2 charges. If you have 2 positive charges, they repel each other. So if you start with them right next to each other, they have a certain amount of potential energy because the minute you let them go, they're going to shoot away. Their potential energy is going to become kinetic and they're going to move away from each other. The potential energy that we say an object has, all it depends on is the height that we measure, and we have to choose a 0 point. We almost subconsciously choose the 0 point to be the ground where it's going to hit, where it's going to stop moving, where gravity can't do any more work to it. But we're going to do something called a roller coaster problem. And basically in the roller coaster problem, much like a roller coaster, you can choose different points and find the potential energy at all these different points. And you're going to have to choose one of them to be 0. Potential energy has to be measured from a 0 point. Otherwise, it makes no sense, right? You have to choose a change in height to get a change in potential energy. So, like I said here, we can say it has 100 joules of potential energy relative to the ground that's 10 meters below it, but it's not physical energy, it's potential energy. It's energy that it will have if we release it and let gravity work on it. Hope that makes sense to you guys.
Do you like phrase it like potential energy is like potential kinetic energy?
No, they're different, so you don't want to do that. potential energy is just the amount of energy that you would get if you let gravity do work on it. That's the best way I would say it. And because the change in potential energy, the change in kinetic energy is the change in potential energy with a negative sign. So if you gain potential energy, you lose kinetic energy, because 0, from this equation, you can see that 0 is equal to the change in kinetic energy plus the change in potential energy. If one of them changes, the other one decreases, or if one increases, the other decreases. An increase in kinetic energy results in a decrease in potential energy, and vice versa. It's weird, I know. Let's talk about this with respect to an Atwood machine using energy. We didn't have this on the test, but an Atwood machine was 2 masses over a pulley. And the idea here was that we could draw the free body diagram. If this is a massless pulley, let's say that it's going to, M1's going to drop and M2 is going to rise. And we could have done all this fun stuff where we said, okay, M1A is M1G minus T, and M2A is T minus M2G. Combining these two, I get M1 plus M2. A is M1G minus M2G, blah, 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 blah. But we've already seen that we don't have to do all these steps. Just looking at the Atwood machine, I'm going to choose that when it starts, M1 and M2 are both at their 0 positions. And then once they fall, I don't know, let's go 10 meters. That will be position 2. And once this has gone up 10 meters, and you have to kind of pretend that there's enough room for them to go up 10 meters. If these things start from rest, so this is 0, this would be minus 10, this would be positive 10, and V initial is 0, V initial is 0. So what I can do here is I can write M1 V1 initial squared over 2 plus M2 V2 initial squared over 2 plus M1 GH1 initial plus M2 GH2 initial is equal to M1 V1 final squared over 2 plus, stop, plus M2 V2 final squared all over 2 plus M2 GH2 final plus M1 GH1 final, and since those are equal. Now, I already said that it started from rest, so these go away. And I claim that these were both 0, so those go away. And that leaves me with all this stuff. Now, I'm going to have 0 is equal to M1 V1 final squared over 2 plus M2 V2 final squared over 2 plus M1 G Y1 final plus M2 G Y2 final, all equal to 0. Now, I know that these are both 10, right? And minus 10. And these have to be the same, but minus. So V1 final is equal to minus V2 final. And H1 final is equal to minus H2 final, right? So what that tells me is that I get M1 minus M2 over 2. Actually, let me do it this way. So M1 times minus V2 final squared over 2 plus M2 V2 final squared over 2 plus, I said that this was minus M1GH plus M2GH. Now, I can move some stuff around here. This doesn't matter, so I'm going to leave, since these are both V, right? This becomes M1 plus M2 over 2 times V squared. They have to be the same. We learned that already. I'm going to move this over, so my negative signs are going to flip. M1 minus M2 GH. And what I see here is that I get V squared is equal to M1 plus, M1 minus M2 over M1 plus M2. Divide this by GH. Actually, I take that back. Divide this by H and leave the G. Why am I doing this? You'll see, and I also have a 2 there. So from this, and I'll go back through it slower in a minute, but from this I get V squared over 2H is equal to M1 minus M2, M1 plus M2. Looking at that, V squared over 2H is equal to M1 minus M2 over M1 plus M2 times G. This is really V final. V final squared minus V initial squared is equal to minus 2, nope, is equal to 2A Y final minus Y initial, but this is H and this is 0. So what I get is that A, and this is 0, A is equal to V final squared over 2H. That means that this is equal to my acceleration. Now, what did I do? How did I find this? All I did was I wrote down M1 V1 initial squared over 2 plus M2 V2 initial squared over 2 plus M1 GH1 plus M2 GH2. Set that equal to M1 V1 final squared over 2 plus M2 V2 final squared over 2 plus M1 GH1 final plus M2 GH2 final. All you had to do for this problem. So we said that it was originally, it was hanging at 0, and this is 0. So H2 initial is 0 and H1 initial are 0. Their initial velocity is 0, right? Because it hasn't started moving. And then once it falls 10, what happens? Well, H1 final will be minus 10. It has to be minus because we have to choose Y positive up because gravity is negative down or is down. So H1 final will be negative 10. H2 final will be positive 10 meters. And finally, because they're connected by that rope, I know that V1 final has to equal negative V2 final, which means that V1 final and V2 final are both equal to V. The absolute value of this, I'm just going to call V final on both sides. The negative sign is important in the H's, it's not important in the velocities. So V1 initial, it starts from rest. V2 initial, it starts from rest. I chose H1 and H2, totally separate coordinate systems. I chose 0 to be where they start from. They don't have to be at the same initial height. I can just say that they're both starting from 0 and then figure out what their final height is. This one went from H1 initial to H1 final, which was a drop of 10 meters. M1 fell 10 meters. H2 started at 0 and rose 10 meters, right? So this is minus 10 and this is 10. These are both V final. So this is V final and this is V final. because the absolute magnitude, because I'm going to square them anyway. So what I end up here is I end up with 0 is equal to m1 plus m2 times v final squared over 2 plus m1g times negative 10 plus m2g times positive 10. And I can just pull the negative sign out, and this becomes m2 minus m1 times 10g, right? So from that, I can solve this. If I know m1 and m2, I can solve it for v final. It's not hard. It seems hard, but I would much rather just start this problem by writing down m1 v1. I'm not going to write it all. m2 v1 or v2 initial squared over 2 plus m1 gh1 initial plus m2 gh2 initial, and then set that equal to the final energy. I hope you see that. Sammy, can you still can't turn on your mic? Because honestly, so check this out, Sammy. All you have to do is write down the initial kinetic energy, the initial potential energy here, right? So what is the initial kinetic energy of M1 and M2 in this case, if they start from rest? 0, right? So it's kinetic energy initial of mass 1 plus kinetic energy initial of mass 2. If they start from rest, these are both 0. Does that make sense to you, Sam? Okay. What is the potential energy? M1 G1 H1 initial, M2 G2 H2 initial. Well, here's where it's a little tricky, because you can assume that H1 is 0 and H2 is 0 initially. You can assume their initial heights are 0. That's totally up to you. That would make all of this 0. Now that initial energy has to be equal to the final energy. So what is the final kinetic energy of M1 and M2? Well, it's M1 V1 final squared over 2 plus M2 V2 final squared over 2. Now, V1 is going to be down, V1 final, and V2 final is going to be up. So this one's going to move up. So the kinetic energies, or well, the velocities are going to be equal but opposite, right? The absolute value of them is going to be the same, but they're going to be equal because they're connected by a rope that can't stretch. That means these two things are actually M1 plus M2 over 2 times V final squared over 2. What is the final potential energy? And this is where things get a little weird. Well, this thing's going to drop 10 meters. Because it drops, it has to be negative. So H1 final is negative 10. H2 final, it rises 10 meters. In an Atwood machine, if mass 1 falls 10, mass 2 rises 10. So that becomes negative 10, and this becomes 10. So what you really get on this side is M2 minus M1 times G times 10, or H final, if you want to call it that. And that means that what we have here, Sammy, is we have that kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. This was 0. This was 0 because we chose it to be 0. Hang on. This is M1 plus M2 over 2 times V final squared plus M2 minus M1 GH, where absolute value, well, not the absolute value, where H is just H. That is that massive equation. That's that massive equation. One more time, and this is the last time I'm doing this. Is equal to, so this is the initial kinetic energy of mass 1 and mass 2. This is the initial potential energy of mass 1 and mass 2. Is equal to the final. But there's a whole bunch of stuff here that you need to understand that makes this part is easy to just write down. You can just write down that equation right there, those 8 terms right there, you should be able to just write down. What becomes hard is writing what are the B's, what are the H's. So in the Atwood machine, we're going to assume that initially it's starting from rest. That means that our initial V's are 0. Whatever the final V's are, they're got to be the same because they're attached by the same rope. So this M1 V final squared over 2 plus M2 V final squared over 2, these V finals are the same. Here's the weird part though. Here's the weird part, Sammy, is you can choose where H is going to be 0. So why not make it easy on yourself and choose the initial H for M1 to be 0 and the initial H for M2 to be 0. Even though they're not lined up together, they're not at the same height, you can assume that they're both starting off at 0 in their own coordinates. If we do that, and then it falls -10 meters, this one has to rise 10 meters, then H is equal to 10 meters, and this becomes negative H, positive H. And so what you get out of this is you get that 0 is M1 plus M2 V final squared over 2, not over 2, plus M2 minus M1 G times H final, let's call it. Move that over to the other side and I get M1 minus M2. GH is equal to M1 plus M2 over 2 V final squared. Now here's the part that I want to get through to you guys. If you remember back when we did the old school Atwood machine, wherever this went. In the old school Atwood machine, you got M1 minus M2 divided by M1 plus M2, all times G was equal to A. Just divide through and solve for A here. That, though, is exactly what we get here. Divide through by M1 plus M2. Leave the G, and this is equal to V final squared over 2H. But this, you already know, if V initial is 0, and this is 2A times H, then A is equal to V final squared over 2H. So this is A. The energy equation, what I'm showing you here, is this energy equation that we did. Writing down these 8 terms, the initial and final kinetic energy and the initial and final potential energy of the 2 blocks, all we had to do was write them down. What was hard was, yeah, we had to make sure our signs were right on our H's in this particular problem. But what I'm trying to get through to you is that you don't have to do a free body diagram. You don't have to remember the constant acceleration equations anymore. The only thing you have to remember is mv squared over 2 plus mgh. But you got to do it for everything. And you got to do an initial and a final. You got to pick 2 points and choose them. All right, that's all well and good. We'll come back to that eventually. There is one other type of conservative force, which means there is another type of potential energy that a system can have, and that is a spring. Now, we normally draw this like this. You have a block and it's attached by a spring. Now, the force on the block is going to be kx, but we're going to have to do something special in a couple different ways here. So imagine that you took this block and you pulled it to the right. It's still attached with the spring. What would happen? It would shoot back to the left if you let go of it. And if you pushed it towards the wall, if you pushed it left, if I push it into the left and let it go, it's going to shoot back to the right. And in fact, if there's nothing to stop it, meaning there's no friction or air resistance, this thing's just going to go back and forth forever. It's going to slide back and forth and back and forth and back and forth. So there's a few things that we need to get clear on this. For the spring block system, and you can draw it 2 ways, or there's kind of 2 different I don't know what you call it, 2 different ways to set this up. So in this case, we say that at rest, right at the center of the block, x is 0. And if we push it to the left, this is negative. And if we push to the right, this is positive. So initially, we have to push the block in. So there's going to be some initial, x initial, right? And then the force on the block at any time is minus kx. Now, when you push the block to the left, delta x is negative, and the force is going to push back the other way. So the force is positive, delta x is negative, therefore we get minus kx. The force is actually trying to push it in the opposite direction of delta x, which you can actually think of this as, that means that we've got our force right. If this is negative, then negative negative means that the force is pushing to the right. If I pull it or it travels positive, the force has to be in the opposite direction. Force has to be negative, and yes, F times minus K delta X gives me a negative, okay? So the spring is always pulling or pushing against the direction of motion, just like friction. It always opposes whatever direction the block is traveling. Shouldn't say always, because at the endpoints, it ends up being, when it gets to the point where it's totally compressed or totally stretched, right? If it's totally stretched out or if it's totally compressed, the force is maximum, but we'll see that in a second. Now, what is the work done by this force? You should be able to do this now, assuming that F dx gives the work from x initial to x final. I write negative x initial, x final, kx dx, right? The negative I just took from here, I pulled out. The k is actually a constant too, so I'm just going to pull that out of the integral. So this ends up being negative kx squared over 2 from x initial to x final. Therefore, the work done is negative kx final squared over 2 plus kx initial squared over 2. But we're going to call this potential energy of a spring. And remembering that delta potential energy should give us potential energy final minus potential energy initial. That means the work is minus the potential energy of the spring. So this should be kx final squared over 2 minus kx initial squared over 2, and it's a negative sign. And that is still equal to the change in kinetic energy, which means kx initial squared over 2 minus kx final squared over 2 is equal to mb final squared over 2 minus mb initial squared over 2. Combining like terms on each side of the equation, mb initial squared over 2 plus kx initial squared over 2 is equal to mb final squared over 2 plus kx final squared over 2, just like we did with gravity. So whenever the spring moves away from equilibrium, we choose a point. Now, let's say that we pull it. So this is x is equal to 0. This is x is equal to 0. This is going to be x is equal to minus 5 meters if you want. X is equal to plus 5. So what we're going to do is this is A, this is B, and this is C. We're going to look at these 3 different energies. If we pull it to 5 and B of A is 0, so we pull it out 5 meters from equilibrium and then let it go. What is B when it goes to B? What is B when it gets to C? What is the potential energy of the spring when it gets to C? And what is the potential energy of the spring when it gets to B? And what is the initial potential energy? So at point A, we have mVA squared over 2 plus kxa squared over 2. This, if m is equal to 2 and k is equal to 50 newtons per meter, 2 kilograms. Now, when we pull it, before we release it, V is 0. This is kinetic energy. This is potential energy of the spring. It's all potential energy. K is 50. XA was 5 squared over 2. That's 25. Divided by 25 times 25 is what? 625. There are 625 joules of potential energy stored in the spring before you release it. That potential energy is going to become all kinetic at B. Why? mBb squared over 2 plus kxb squared over 2. The thing you have to always remember with springs, you have to choose 0 to be at equilibrium of the spring. When the spring's sitting there and it's not being compressed or pulled, it's just at rest. We say the rest length is when x is 0. At that equilibrium point, there's no force from the spring. So there's no kinetic or potential energy from the spring. So xb is 0. That goes away. And we get mvb, which would be 2 vb, we don't know, over 2, which is vb squared. But energy is always conserved, which means the energy at position A, the energy at B, and the energy at C are all equal. energy at A is equal to energy at B is equal to energy at C. That means that mvb squared over 2 is equal to kxa squared over 2. Now I knew that kxa was 625 joules. 2 over 2, I said the mass, so this goes away. So VB is square root of 625, which happens to be 25 meters per second. Is it positive or negative? It doesn't really matter, but in this case, it's moving the opposite way because I started at A and I released it. And then finally at C. At C, it's fully compressed again, and V is 0. Whatever you pulled it out to, all the potential energy is going to be stored here. So kxc squared over 2 plus mvc squared over 2 has to equal the energy at A, but we know that it comes to rest. Where does it come to rest? Well, when kxc over 2 squared is equal to kxa squared over 2, k over 2 cancels and you get xc squared is equal to xa squared. Take the square root of both sides. You get that xa is equal to minus xc. Without all this mess, what we have is, we have the energy at A is mva squared over 2 plus kxa squared over 2. But that is equal to the energy at B, which is mvb squared over 2 plus kxb squared over 2. But that is equal to the energy at C, which is mvc squared over 2 plus kxc squared over 2. When it is at full compression or full, when it's stretched fully or compressed fully, if xa and xc are max x, v is equal to 0 at max. So when you stretch it out the maximum, or if you let it slide back and forth, when it reaches maximum compression or maximum stretch, v is 0, therefore these go away. And when at equilibrium, x is equal to 0, so that means xb, which occurred at 0. And look at this. This was all potential energy, all kinetic energy, all potential energy. So let me I really don't like the videos they have for their springs. I thought they had a better one. Maybe they do. Hang on a second. Okay, so nope, these are not the ones I want. All right, so stopping that share, and I'm going to share this screen with you. Okay, so here's a spring at equilibrium. It's going to start moving to the right. You can adjust the mass on this, but see how the force pulls it? So hang on, let me pause it for a second. Okay, so what this is showing you is right now there's no force on it at all. And right now the energy, I don't know why they're showing. So this is, oh, the energy is 0 right here. There's no potential energy. It would be all kinetic energy. But what this is showing you is the purple arrow is kinetic and the red is spring. Or so the red is potential energy due to the spring. The K is kinetic energy. So when it's at equilibrium, it really should be at 0. The reason why is the way they program this. But it goes to maximum stretch, maximum distance away from the equilibrium point. It has all potential energy of the spring. When it's at here, it's 7 meters. It then heads the other way. All that potential turns into kinetic as it crosses through the equilibrium point. It no longer has any potential energy at the equilibrium, all kinetic, until it slides back to wherever this is, I guess -7, all potential again, slides back the other way, back and back and back and forth. So just watching this and watching what the potential energy and kinetic energy, how their one form is changing to the other, you get this nice motion back and forth and back and forth, always to the same distance, because there's no friction or anything else in the problem. Potential energy turning to kinetic, kinetic energy turning to potential, back and forth, back and forth, back and forth. Now you might think that's not super important. I mean, how many times in life are you going to be looking at a spring? But it turns out that this is actually a central force. And central forces, which springs mimic nicely to learn about, actually occur everywhere in nature, all over the place. You're going to see this everywhere. This is something called simple harmonic motion, actually, where things will go back and forth and back and forth and back and forth. It goes from cell biology to electrons in quantum mechanics to photon effect or photoelectric effect to everywhere. You're going to see what is called a restoring force, and the spring is a restoring force. So we have, as I explained, potential energy due to a spring is kx squared over 2. Kinetic energy is mv squared over 2. And just like with gravity, it's conservative, meaning that if the only force acting is a spring and the only energy you have is from the spring's potential energy and the kinetic energy, then the energy is always a constant and it's always conserved, which is nice. So at maximum positive displacement and maximum negative displacement, when x is maximum, then you get 0 velocity. When x is 0, the velocity is maximum. We know all that. However, now we have a cool, fun new problem. And this cool, fun new problem is going to use everything we've learned. So imagine you hang a mass from the roof, and this is the rest length of the spring. You pull it down and you let it go, and it comes back up. Okay, so you let it go and come back up. So we're going to assume that this is when x is 0, and this is going to be when x is 6 meters. I know 6 meters is 18 feet, be a very long spring. But what we want to know is what is the velocity when it gets down to here? We don't know how far it's going to go. Let's say this mass is equal to 2 kilograms and K is 600 newtons per meter. What do? So this is our 1 and this is our 2. And we're assuming that we started here from rest. So V here is 0. All we have to do here is write mv squared over 2 plus m1 gh1 plus m k x1 squared over 2, and then rewrite them again for 2. mv2 squared over 2 plus m, I don't know why I wrote m1, gh2 plus kx2 squared over 2. Now, we know that we can call h whatever we want. Let's call it 0 as well, and 6, or maybe instead, maybe this distance is 2 or something, 2 meters. So we could call this h2 and h8, doesn't matter. We're going to leave them the same, but know that normally h and x have nothing to do with each other. Usually, well, I shouldn't say that, but you'll see with like a pinball problem where they don't really. if this started from 0, that's 0. Since I chose H1 to be 0, that's 0. And it's at equilibrium, so that's 0. So 0 is mv2 squared plus mgh squared plus kx squared over 2. Now, I want to solve for v2. I want to know what v2 is here. Move those two over, I get mv2 squared over 2 is equal to minus mgh2. And keep in mind, this should be a minus 6. Minus 6. And minus kx squared over 2. So this becomes positive because h is going to be negative. If I multiply through by 2 over, well, let's leave it negative. If I multiply through by 2 over m, then I get that v2 is equal to square root of negative 2gh2 minus k over m x2 squared. Now, h2 is a 6, so that's 2. Oh, this is not going to be good. I don't want to do that because I end up with a negative inside the root. Oh, nope. I'm done. Kx is going to be positive because we're going that way and the force is going to push up the other way. Is it? No. No, I'm wrong. I'm dumb. It's not going to be positive. It's going to be negative. So what am I going to do about that? Yeah, that's obviously not going to work. And the reason why it's not going to work is that I'm going to get a negative sign under the root. Yeah. Just because I chose too big of numbers. All right, so let's say this is...
It doesn't matter which number we choose because all of them are negative number. And
right.
Each number we choose, we couldn't get the number because all in the...
Yeah, we get a negative sign under the root. So what I'm thinking I should do is I shouldn't have made it x so big, number one. Yeah, and yeah, in general, I've just made these too big. So let's say instead that this is going to be negative 0.6. And I'm going to make this 60. You have to be careful with these because you can just plug numbers in and then things don't quite make sense. So negative 0.6 meters. And that would give me 2 times 9.8 times 0.6. 2 times 9.8 times 0.6 would be 11.772. And then K over M would be 60 divided by 2, which would be 30. 30 times 0.6 times 0.6, which would be 10.8. And then I would get whatever that is, 1 or 0.472. So square root of 0.472 is, this would be positive or negative 0.687 meters per second. So the point here is that just like with gravity, you can write mv squared over 2 plus kx squared over 2. So this is the energy at some point A, right? all you have to do is write this down and then find the energy at point B. Okay, XB squared over 2 plus MGHB. And then you can set them equal to each other because everything here is conserved. The potential energy turns into kinetic energy. The kinetic energy turns back into potential. Another way of seeing this is the change in kinetic energy from A to B is equal to the negative of the change in potential of spring from A to B minus the change in potential energy of gravity from A to B. That's all that's happening here. Any change in one changes the others. And then you really only have, you're usually given K, although sometimes you're not given K and you have to find it. But you usually are given K. Sometimes you have to find either V, X, or H. You almost always need to go through and write down what is VA, what is VB, what is XA, what is XB. I'm not going to make you, well, I might make you once just to make sure you know how to do it on either a quiz or on an exam. But really, you can look at the system and go, okay, I know VA and I know VB initial, or I'm sorry, VA is initial, VB is final. And you might need to figure out what H or X is. You might need to know something like with the, what was it, the Atwood machine, where you know that VA and VB or V1 and V2 or something are equal. But the point is that you can just write this equation down. This is the equation for energy. There's a lot of stuff in there. There's the potential energy of a spring. There's kinetic energy. There's potential energy of gravity. But really, that's all you have. And you can write this equation right here every time. You can just set the energy at point A to the energy at point B, and you're done, as long as you know enough variables to solve your problem. That's it. This is all there is to it. All there is to energy except for friction, but we'll get there. And we're going to do a whole bunch of problems, not just on Thursday. We're going to do a whole bunch of problems with energy. Some of them are super easy, some of them are not. So we got this stuff. The algorithm here for gravity and spring only is, like I said, let EA, EB, EC all equal each other. You write down this equation, set it equal to EB, set it equal to EC, and you're done. You do have to choose where Y is 0 for every single mass. You do need to choose where X is 0 for the springs, not choose. You need to know where X is 0. 0 is the equilibrium point. So if you're told it's stretched 3 centimeters from equilibrium, you know that XA would be 0.03 meters, right? All right, so we only have a couple of things left, really 2 things left. This isn't as important. We'll talk about this more when we do some problems with power. But power is, if you have work, right? And work we said was F dot D. What do I get if I take a time derivative? If I want to know how the work changes with time, well, I get F dotted with D times d dt. And this is known as the power. Now, if F and D are parallel to each other, remember that this is just d dt of, let's call it F and X. Well, if F is constant, then this is dx dt, and this is F times the velocity. So the force times the velocity is the power, and I should say that this is really average because it's constant. Instantaneous at any time is really ddt. But we usually just say that the power average is the change of work over time. or change of time, if you like it that way. That's all you need to know about power, is that the power is the change of work with time. So when we talk about like how much power a drill uses, we're talking about how much energy it uses in a set amount of time, the energy usage per time. We'll do a couple equations on it. Power, though, is the easiest of the plug and chug. Read that section. There's like one quick question involving power as force times velocity, where I think, or at least there used to be, where they would have a jet that's moving at, so a jet that has a velocity of 300 meters per second, and its engines put out a force, a thrust force of 4,000 newtons. How much power is it using per second? 4,000 times 300, which is 12 times 10 to the fifth, or 1.2 times 10 to the sixth. The units of power are watts. They're a joule per second. Watt was another famous steam engineer. But there's really not a lot to power. It's just the time derivative of the work. And really, power is pretty useless. It's impressive, but it's not that useful, to be honest. Power is also a little bit weird because the sign of power doesn't matter. Imagine it this way. If I'm running a drill to drill a screw into a wall, and the drill's putting it into the wall or taking it out of the wall, it's still using the same amount of power because the derivative is energy with respect to time. That's a scalar. And so here, you know that power is force dot velocity, so that's a scalar. So again, just like with energy, negative power doesn't really mean much. It means less with power than with energy, because at least negative energy, if we're talking about work, means we're slowing down. Negative power, I guess, means you're slowing down. I don't know. I don't think negative power means anything at all. But you can definitely get negative power. It's weird. The final thing that we have to talk about is external forces. And when we talk about external forces, what we really mean are non-conservative forces. The only non-conservative force we know, the only external force we really know, is friction. So let's go back to our handy, what is work? Work as an integral from x initial to x final is the force times dx. If the force is mu times n, and for simplicity, I'm going to use mg to be n here, but if you were on an incline, it would be mg cos. So this becomes, and it does have a negative now, where before we were dropping it because we were figuring out the direction. In work, it has a negative, just like mg does. So this is negative mu mg dx, which becomes negative mu mg x final minus x initial, or mu mg x initial minus x final. Now, this is the work. And remember that most of the time, we assume x initial to be our 0 point. So friction's always going to do negative work. It's always going to result in a change of kinetic energy that's negative, meaning it's always going to end up slowing down our system, which is exactly what it should do. However, there's a weird problem here with the fact that where do we put it? We said that EA in, let's assume that there's a spring. So this is MVA squared over 2 plus KXA squared over 2, MVB squared over 2 plus KXB squared over 2. And now let's say there's friction. where do we put the friction? And this is where things get messed up, because we normally say EA is equal to EB. I'm going to actually change this and call this E initial and E final. And you'll see why in a second, because it's actually better to do it that way. So if this is initial and this is final, this is initial, this is initial, this is final, this is initial, final is usually what we say. But now we have this work of friction that we have to put somewhere. I'm going to actually do this just to make it easier. Work of friction is equal to minus, absolute value. Because I want to make sure that the sign's right, and then we'll talk about that in a minute. So you can imagine that if initially you had 100 joules of energy and you lost 20 joules of energy to friction, you would have 80 joules left, right? So minus 20 joules. So this is the work of friction is negative. This is my initial energy, and this is my final energy. So you have a choice here. You can either say the initial energy minus the work of friction is equal to the final energy, which would mean mv initial squared over 2 plus mgh initial mv final squared over 2 plus mgh final minus mu mg. Or you could move it to the other side. You could say E initial is E final plus work of friction, which would mean same thing that we did here, but now it's really important though that you understand where to put friction, because energy is not conserved anymore. And for whatever reason, it tends to throw people, it looks wrong, like you're adding energy to the final side, but you're not. It should be the final energy plus the work of friction, all added together should have given you the initial energy that you had. That's all. So when we add in friction, whenever we have friction, we have to add it. As you can see here, E2 is equal to E1 minus the work of friction, or E1 is equal to E2 plus the work of friction. When I say work of friction here, I mean mu n, not negative mu n. I mean mu n. So E1 minus mu n is equal to the final energy. E1 is equal to the final energy plus mu n. It's a little weird. We'll go through it. We're going to do like 4 problems on Thursday with friction. And they'll all work together. So the only other thing that I want you to go through before Thursday is there's a thing about potential energy diagrams. I'll show them to you really fast. They're a little weird. You're not going to be tested on them. I don't even think I gave you homework on them. But they are in 8.3. So in section 8.3, if this will pull up, 8.3 is all about reading potential energy diagrams. The point of potential energy diagrams is that, and I think I just passed one there. Where is, okay, reading a potential energy curve. So this is a potential energy curve. It shows on a graph, at 0, you have all kinetic energy. And as you go up, you gain potential energy. You go from 0 potential energy to, I'm sorry, you go 0 potential energy to all potential energy. So what they're showing here is that the mechanical energy is 5. That means if you add the potential energy and the kinetic energy of the particle or system together, you get 5 joules. Now, that also means that the most that the kinetic energy could be is 5, and the most that the potential energy can be is 5. So what they're showing here is that basically all the energy has to equal 5. So if the potential energy is 1, the kinetic energy is 5. When you get up to here, the kinetic energy is 0 because the potential energy is 5. Remember, they can share it. Here, when it gets to x5, it would have a potential energy of 4 joules and a kinetic energy of 1 joule. So it could escape. Now, the point of reading a potential energy graph, which is what these 3 are, is that these are wells. Now, imagine if this gray line were actually at 2, which means the most kinetic energy it could have here would be 2 joules if I move this gray line down to 2. And that means it could never get out of this well if it was at x2. If it had 3 joules of mechanical energy, 3 joules of total energy, it could get to x3 right at the top. Let's say it had 3.1. It could actually go back and forth from around whatever this would be, the point where the potential energy is 3.1 joules to where the potential energy is 3.1 joules. It can go back and forth between those 2 potential energies, constantly exchanging potential energy and kinetic energy for each other. But it couldn't get out. In order to get out, it has to have at least 4 joules of mechanical energy. So if it had 5 joules here, anywhere greater than x5, it would have a joule of kinetic energy. mv squared over 2 would equal 1 joule. And it could get away as long as the mechanical energy, the total energy of the whole system, were 5. This is showing you the force, and the slope, the negative slope of the force graph is the potential energy. All right. So they're saying that at 5 joules is a turning point, because once it hits there, it doesn't have enough energy to go any further to the left of x1. It turns back and heads to the right. So a lot of times what we'll see is as it comes in from the right to the left with a certain amount of energy, you draw these potential energy curves to see what states it might get trapped in. And you'll see these a lot more when you do like physical chemistry, quantum chemistry, higher level physics. Potential energy curves are the only thing to remember to read is that it usually shows the maximum mechanical energy, and all you do is you figure out whether or not it can get out of a trap, out of a curve, or a well, as they call it, by comparing the total mechanical energy and seeing if it would have enough energy to get above the well. At 1, it can't get out of well 1. At 3 joules, it could go between the 2 wells. At 4 joules, if 4 is just a little, or if the energy is just a little bit less than 4, it will never get to x5. But as long as it's 4 or better, the particle can escape and to the right. And if it's 6 joules or more of mechanical energy, it can escape to the left. So a lot of times they'll draw like the energy of different molecules in chemistry. They'll draw them on these potential energy curves to show you the different energy states of the molecule in, say, a gas or a reaction or whatever, and to show you what's allowed. We're not really going to go over it because honestly, reading a potential energy curve is something that once you have to do it, you'll figure it out really fast. But I want you to do it. I want you to read it. There's a couple of, I don't even know if there's a problem here that you can try. Um, do. At x equals 6.5, the particle has kinetic energy. So here the kinetic energy would be 16 joules. Why? Because here it has 0 potential energy, but it has 16 joules of mechanical energy. Mechanical is potential plus kinetic. So all of it is kinetic. And at x is equal to 4, how much kinetic energy? Well, if it has 16 joules total and 7 of it's locked up in the potential, 9 of it is available for kinetic. That's all that you have to do. There's a couple of quick problems there for you. I don't really think it's all that important for us to know at this point. And like I said, when you have to learn about these, you're going to learn about them. And they're not hard to learn. So next time, if you go to our modules, so if there was stuff you didn't understand, read through the book, and that's great. I think you're going to learn more from doing it. So next, on Thursday, we're going to do it. So I've got this chapter 7 and 8 problems PowerPoint, and each of the problems has the answer for you if you want to try it yourself, and then a couple sheets of blank places on, or blank slides so that we can work on the solutions. But I think there's like 12 or 14 problems here that I'm going to go through and do all of with energy. So remember, you want to do it with energy. Some of them are fast, some of them are not. And then you also have homework, and the homework isn't too bad, but we'll go over kind of anything tricky on the homework next time on Thursday as well. So give this a shot. For example, the energy at A, B, and C, all you write down is mgHA plus mBA squared over 2. Set that equal to the energy at B and the energy at C. And it's super simple to figure out what the different velocities are because they gave you the heights. Stuff like that. This stuff isn't really hard, and once you do it a couple times, it's actually pretty fast and fun. It's a lot funner than drawing free body diagrams and remembering equations. So anyway, good luck. I'll see you on Thursday. Remember, the president will be here, so if you can, be on time, please. And otherwise, I'll try to have your exams graded by Friday.
Excuse me.
Yes.
I have a question. Do we have quiz next Tuesday?
We will have a quiz next Tuesday on energy.
On energy, on chapter 7 and 8 both?
Yeah, 7 and 8 are really one chapter. I don't know why they split it up the way they do. I think that the only thing they change is they add the conservative forces with friction. But you'll see when we'll deal with that on Thursday. I'll do a couple problems with friction. It's really easy to do friction.
Okay. And the other question, do we have a lab this week?
No, we don't have lab this week. I think we never were scheduled to have lab this week. So your lab isn't actually due this week. It's actually due.
Yeah, the previous lab, but we don't have the.
Yeah. You
Can
still have that lab on inclined plane. So.
Yeah. Can I have a question about the exam, or you don't have time now?
No, I can answer a question. What's up?
The question, I see the answer that you gave us. The question 1, number E.
Oh, where did it go? Yeah.
You said that the T in the answer sheet that you
Is that yeah.
Yeah, the T, you put the G, but it is after the parachute is opened, and the T, I think that we should use A instead of G.
Yeah, actually, you're right. So this morning, that was bugging me. This morning, I was actually on my phone while I was writing this,
Oh, yeah.
and I realized I was like, you can see that I erased something?
Yes.
Yeah, thank you. That was so bugging me. That is wrong. Yeah, it's 5.42.
16.13. And
hang
we
on.
should put 3.3 instead of negative, instead of G in the T, in the E part.
Yeah, that would be so 54.25 minus 0.4 divided by 3.3 gives me 16.318.
16. Yeah.
And then
And
so the height,
the F part is also changed.
right? Yeah, the height changes because it's,
No, the height doesn't change. The F part, the total T.
I'm sorry, what?
The total T, total time in the F part.
Oh, yeah, okay. So hang on one second. 54.25. So I got 16.32, let's call it.
That's 5 point.
And then 54.25 times 16.32. 3.3 times 2. That's where I messed up. So that seems way wrong.
The total time 21.83.
Oh, the
something.
height.
The height is correct.
5.42 times 2 plus 4.25 times. No, the height is wrong.
No, the height you should put 3.3 and instead of G. You should
Yeah.
put A and it, but it only changed later.
So is that what I'm doing? That must be what I'm doing wrong. 54.25 times 16.32 plus 9.81 times 25 times. Nope. I keep doing that same stupid thing. 3.3. Oh, right. But it's positive 3.3. So times. I know what I did. Okay. Yeah. So yeah. Okay. So this is weird. Yeah. The time would be 21. So I knew that the height was 446 when I wrote it, because I essentially basically made it 600 meters. And then this morning I was on emailing with the other professor in my other class. And when I put the 16, I forgot to put the negative sign or the positive sign for 3.3. So I got this really ridiculous number, like 2,200 meters. And I was like, I know that's wrong. So, and I looked at it and I was doing other things. So I'm just done. You guys are right. I'll fix it and resubmit it.
The last question, last part.
Uh-huh.
I understand why you gave us this answer, but the question is not clear. You
Right.
thought that it is constant velocity.
Right.
But it doesn't say that it is in constant velocity because in the question it is not constant velocity, but in the F part you say it is constant velocity.
Right. So
the question doesn't say anything about constant velocity.
Right. No. And so what I want you to do in this problem is I wanted you to write these equations for part C.
Okay.
Assuming everything. Once you have these equations, constant velocity says that all these A's are 0.
Because it doesn't say in the G that it is constant.
No. G is not constant. It's not. The reason why this is 0 is simply because of the numbers.
I assume in the G that it moves to the right. I assume. And I got the A 0.25.
Yeah, and that's okay. If you got 0.005 or whatever, that's fine. Because what I did was I used mu k, I used a third in my answer. And
Oh,
so with that third, I get 0. If you got a positive
Oh,
to the
because-
right number, that's okay.
oh.
It was
Yeah, I
just,
got the positive, a little positive number,
Yeah.
and I said that it
Yeah.
will move them. My assumption is correct.
yeah, no, your assumption is totally correct, totally fine.
Oh, okay.
If you give me a little bit to the right, that's fine. If you
A
give me
little bit to the right, yes.
it's fine too. But
Oh,
yeah,
okay, thank you.
you're not going to get counted off for saying it's a little to the right. I realized I should have just said, oh, it's a third, but
Yeah.
I tried to make it easy on you guys so that you would realize, oh, this just ends up being 0. It can't move. And it can't go the other way without the force because there's no way it could. It would
Oh,
try to pull the
yeah,
other way. So
I understand. I
thank
thought that yeah, I got your idea. Yeah, thank you.
yeah, so thank you for telling me about the time. Like I said, I was distracted this morning when I wrote this up and I was dumb.
It happens.
So,
It
did I
happens a
do it
lot.
right? I did this right. This one's right.
Yeah, it is correct in the right side, but
but
the T
The
side.
time is stupid over there.
Time.
Okay. Thank you guys.
Thank you. Have a great day. See you later.
Yeah, Hamid, it's fine. As long as you got to the right, it's cool.
Yes. Thank
I
you.
assume.
See you later. Bye.
Bye, everybody.